So, good morning, everyone. Today, we are going to be discussing primarily macroscopic momentum balances. But first, there is one or two things I'd like to address and point out. This is a little bit of a mess. Regarding Bernoulli balances. So last time we had discussed a couple applications. We looked at tank draining as well as pitot tubes. But one other thing that I always like to mention is the concept of the head of a fluid or fluid head. And so when looking at the mechanical energy balance for a fluid system, we write this expression, which denotes the key energy terms associated with fluid flow. We have kinetic energy, pressure energy, static potential energy, work, and friction. Now, if we divide each term in this system, or this equation, by gravity, something intriguing happens to the expression. Primarily, if we look at the units of each term, the units simply become a length. And what this is the mechanical energy balance in the form of fluid head, where, oh crap, wrong button, excuse me. Each term now becomes an energy terms in terms of fluid head. So the velocity kinetic energy becomes what's known as the velocity head of the fluid. Then we have the pressure head. Then we have our static head. Work is known as the head added. And this friction over G is known as the head loss. And so what this does is we can describe each of these energy terms as a function, as a form of a length. And so what we can do is, if we're looking at a system outside of work and friction, we can designate everything in terms of fluid head. And it gives us an interesting implication. Meaning, if we're looking at a system with no work or friction, and we look at a comparison between 2 points as we've done, we find that the energy at point 2 is equal to the energy at point 1. Or the fluid head at position 2 is equivalent to the fluid head at position 1, which means for these systems, the change in fluid head is 0. And so if we're looking at any system, the change in fluid head is simply the work done on or by the system plus the friction over gravity, which indicates that we have work done or on, and oftentimes the friction is designated H sub L, which stands for head loss. And so to quickly summarize, we designate fluid head because it makes things a lot easier to discuss in a very strict term in terms of feet Everything's in the form of a length, which is easily, when you consider, static head in terms of how much energy is associated with that fluid, that we could easily translate into a visual potential energy. From that, you can identify in any sort of energy balance, what is the change in head necessary in that flow system as a result of both work that must be done and as well as expected head loss or energy losses by the fluid in the system. And this becomes important because when we look at fluid transfer equipment and pump and compressor design and operation, a lot of times the way it's described is in essentially fluid head term, where we end up looking at pump and compressor curves that is a function of both the flow rate and the fluid head that can be added by that piece of equipment. And so it's important to understand where these terms come from and how they relate to the energy of the fluid itself. Are there any questions?
Actually, yeah, Dr. Lopez. So is fluid head always expressed as a capital H, and we'll just have to differentiate with context that it means fluid head and not enthalpy?
Yes. Yeah, it is. I've yet to see it not be denoted as an H. That's just one of those things. If only the English alphabet had more letters, engineers and scientists would be able to speak in clearer terms. To be honest, for the longest time, I described flow rate as Q, which got really bad when we started talking about heat transfer because heat transfer is also as a Q. And so over the years, I've adapted to a V dot to make them easier to differentiate. But yes, total head is always as an H, and it usually has lengths, feet, or meters. And a lot of times it'll be feet and meters of fluid. Because if you look at the energy term, particularly the static energy term, it doesn't matter what fluid it is. The energy is simply just height times a gravitational constant. And so by doing it in terms of just generic meters, you can kind of understand the energy implication without actually knowing any fluid properties at all. Right? It almost feels kind of quantized. Any other questions? That was an excellent question. If not, then let's switch gears and start delving into my momentum balances. Particularly today, we're going to look at macroscopic momentum balances. Next week, we'll touch base on microscopic momentum balances. But as microscopic momentum balances are more applicable for graduate level systems, I tend not to put too much emphasis on them. So if we recall from physics, momentum, which I try to designate as fancy M, how do we typically calculate the momentum of a system?
M times V.
So the mass of any sort of system or object times its velocity, which for this class I designate U 9 times out of 10, right? So it's just a mass times velocity. And so if I'm looking at a momentum balance, what I'm most interested in is understanding the implications for changing momentum as a function of time or distance. Which means in this system, I'm interested in looking at the differential of this quantity, mass times velocity, with respect to time. Now, I can distribute the derivative, and what I'm left with is mass times this change in velocity with respect to time, plus velocity times the change in mass with respect to time. And so what this means is it gives me the implication of two types of systems. This system correlates to mass times the derivative of velocity with respect to time, which is acceleration. This term denotes the influence of a system at a constant velocity or a mass at a constant velocity, but changing or moving in and out of my system with time. And so I designate this part U times, oh, there it goes. Hold on, I have to bring it back from the grave. I apologize again. M dot U. And so what I'm left with is dm dt, which is fancy m dot, equals mass times acceleration times my mass flow rate times the velocity. Which means I have two different contributions to a given momentum balance. Mass times acceleration implies I'm looking at forces within my system. Mass flow rate times velocity indicates I'm looking at convective flow, which with it brings changes in momentum to my system. Which means if I'm looking at, let's say, fluid in a pipe, and I draw my little system box, I'll make it blue, it's easier to visualize. I have to consider what are the forces involved and associated with flow moving in, flow moving out, as well as what are the forces involved associated with the fluid within the system, whether it be a function of gravity, and we can also consider what are the implications of pressure on the system. So we have to consider what are the forces involved with the fluid flow, and how does the flow convection or fluid flow itself influence my momentum flow or my change in momentum. And so what this means is if I look at momentum with respect to time, I've already designated as m dot. And so I can look at m in minus m out plus the sum of I equals 1 to n of any forces involved within my system. And just like mass and energy in the systems that we deal with, we have to consider the implications of conservation of momentum. Meaning, if we're not having any sort of net acceleration or physical motion of the system itself, momentum must be conserved. And in systems where momentum is not conserved, that must result in some form of net resulting force and resulting essentially acceleration of our system. So let's consider an example, which is in this image that I'm showing here, which is flow through a pipe. If I make my system some volume element of my pipe, how can we derive a momentum balance for the fluid flowing through the pipe as shown below, considering all the forces that are shown involved in terms of convective flow, pressure, and shear stress that's being exerted in this system. So if I were to draw this system, this is my flow direction. And once again, I'm going to define my system as this element. Then I have to consider, well, the forces that I have. I have shear stress, which is resisting the flow, which is primarily existing at the surface of the pipe or at that solid fluid interface. I have pressure being exerted on my system by the fluid just outside of my box. And I also have convective flow, mass in, mass out, because my fluid is flowing both into and out of my system. So with that in mind, if I was going to create a momentum balance, which once again, I'm looking at momentum in, momentum out, plus any forces. And also keeping in mind that pressure is essentially a force applied over an area. So if I'm interested in the force itself, I have to multiply my pressure times an area. So what I'm left with is I'm looking at the pressure in minus the pressure out times the area in which it is exerted, which in this system would be the cross-sectional area, or pi times d squared over 4, plus the mass in times the velocity, minus the mass flow rate out times the velocity, minus the shear stress, which is happening at the wall, times the area, because it's just like a pressure, it's a force acted upon an area. But for shear stress, the area on which it acts is different. It's primarily acting on the surface of the pipe, which in this instance would be pi times the diameter times the length element of the pipe, which in this sense would designate the change in momentum over time, which would be 0. Because if it wasn't 0, this pipe would be moving and we would be having a lot of issues. Which I don't know about you, but I don't want my pipes to move in my plants. So the good news is the mass flow rate in and out of my system by the mass balance has to be constant. So what does that leave me with? Well, that tells me that the pressure in minus the pressure out times pi times d squared over 4 has to be equal to the shear stress acting over its surface. Which means if I wanted to solve for shear stress, I can divide pi dl. And what I'm left with is pressure 1 minus pressure 2 times the diameter over 4 times L, which allows us to determine shear stress for fluid flow as a function of pressure drop. and vice versa. It describes why pressure drops. A pressure drop must exist within a fluid system, right? Because the shear is exerted, which removes energy as a form of friction, and so the pressure falls. Any questions on how I was able to derive that momentum balance on our fluid system? So I looked at flow coming in and out and how it brings its momentum, and then I considered the forces, which in this case would be pressure and shear stress.
I actually
Now,
have a question, Dr. Lopez.
go ahead.
So I understand how m dot in is a positive in the equation, and then m dot out, that's a negative. But how come P2 is negative when it's like going into the system, the same thing as P1?
That's a very good question, and I was honestly expecting it. And so with just like velocity and acceleration, momentum is a vector. And so its direction determines its sign contribution to our system. And so what we're really looking at is an x direction momentum balance. And I would define the x direction being positive to the right of my system. Now, if I were to define it in the negative and to the left, I would end up with the same expression. However, all my signs would be flipped. And so oftentimes what you can do is you can say, okay, what's your positive direction that you're going to be assessing by convention? Most of the time we're looking at to the right is positive, up is positive, and probably out of your system would be positive as well. And so that's a good question. It's also why for this system, I'm not considering gravity, because I'm going to say, well, the weight of the fluid in and out of the system is probably going to be in the y direction, which for this balance would not apply. So that's a very good question.
Clear with that. The mass out is negative because it's leaving the system, but the second pressure, P2, that's negative because it's going in the opposite direction.
Yeah, because it's being exerted in the opposite direction. Okay. Yeah, pressure is interesting in how it's defined. By convention or a good rule of thumb for figuring out where's direction is the pressure going to be exerted. It's for these systems, pressure will always be exerted onto the system, regardless of how it's drawn. And I'll show you. We'll look at an example here in a minute of flow through an elbow or a bend, and you'll see how I define the pressure in which direction. And it's usually just because pressure is always going to be exerted onto the system by a fluid. So let's look at another more complicated example, which in this instance, if you should be able to see this. We're looking at a little trolley, which from this trolley, a jet is being shot essentially at this trolley, which is causing it to move at a different velocity v. So the fluid is flowing in at a particular velocity u with its mass flow rate rho ua, and it's causing this little trolley to move with a velocity v. So the question then becomes, can we write a momentum balance on the trolley shown, which is moving due to a momentum transfer, which is applied by the water jet? So if I was gonna draw this system, I would have it look like this. The trolley has a particular mass, m. The system I'm look at is essentially the trolley itself, and it's moving forward with a velocity v. Then I have a jet being shot at this trolley with a velocity u, with the fluid flowing out at a flow rate of rho UA. And so this is I would definitely argue is one of the trickier problems, because as we're looking at this system, we see there's two different velocities happening in this system. And what that often results in is the existence of two different reference frames that we can solve this balance based upon. So the way we're going to look at this one for right now is we're going to consider the control surface or system is going to be moving with the trolley. So my first question I would usually ask in these types of instances is, can I assume my momentum will be conserved considering the fact that I have a jet being shot on a trolley which is moving at some velocity v? So would you say that momentum is zero or is not zero?
If it's moving at a constant velocity, it would be zero, wouldn't it?
Now, I didn't say it was moving at a constant velocity. If it was moving at a constant velocity, I would say it's zero. But I don't know if it's a constant velocity or not. And for this problem, the likelihood of it being a constant velocity is most likely not going to be the case. So for this system, I would probably consider this to not be a truly conserved system. So because if I'm shooting this, it would be really difficult for this jet to be moving it at a constant velocity, primarily because that jet would have to be moving with it. You understand what I'm saying? Because after a certain amount of time, the trolley's going to be over here, and the jet is going to have some reduction in the momentum transfer. And so for this system, I would argue that the change in momentum would not be zero. And so this would indicate to me that acceleration is occurring in the system. So the question then becomes, how can we solve for that net acceleration? So what I would have to consider is, since I have accumulation of momentum happening in my system, which is causing my trolley to accelerate and move at some velocity, v, which in this instance would be changing over time, I would state that the rate of momentum addition would equal the rate of momentum accumulation. Which means if I'm looking at, just a really overall, I would have my momentum rate in, momentum rate out equals my momentum rate accumulated. which in this instance, there wouldn't be any momentum real out. So I would have rate of accumulation and rate of addition. So I would need to identify each of these terms within my momentum expression. So let's look at the momentum addition or the momentum in. So what is adding momentum to our system?
Would it be the jet being shot at the trolley?
Yeah, so the jet being shot at the trolley is adding momentum. So it's some mass, flow rate of our jet, times what velocity?
Velocity u.
So this is where it gets tricky. It would be velocity u if the trolley wasn't moving. But since the trolley is moving, it would actually be looking at the difference between u minus v. Because if we consider if u and v were equal, if the jet was moving just as fast as the trolley, it wouldn't be able to essentially get into the system, right? And so what we would really have is the mass of the jet times the essential difference between the jet's velocity and the trolley's velocity, which I could write as rho u a u minus v. Now, the rate of momentum accumulation, dm dt. Now, we already said dm dt was equal to m times u d dt, which I can write as m du dt plus u dm dt. Which, and all intents and purposes, this dm dt is going to be my accumulation term. So I have m times a, which is the mass of the trolley times acceleration, which is what we're looking for, plus u times the change in mass with respect to time. So how is the mass of the trolley changing with time? This is actually v, because our system's the trolley. So what mass is being added to the trolley? Is there any mass being added to the trolley? I guess I should ask that.
Is it from the jet?
The mass is being added from the jet, right? So this is essentially the mass flow rate of the jet, which would be rho u a. Let me double check my notes. It's actually as a function of the reference frame. So it would be rho a u minus v. And so if we combine these concepts, what we really end up with is an expression that says rho times a times u minus v times u equals m times a plus rho a u minus v times v. And so if we essentially distribute all these terms, what we should end up with is, let's see if we can do this real quick. So we have rho A u squared minus rho A uv equals m times A plus rho A uv minus rho A v squared. So if we bring stuff over, we should end up with something that looks like this. We have rho A u squared minus 2 rho A uv plus rho A v squared equals m times A. If we factor this, what we end up with is rho A u minus v squared equals ma, which means A is simply rho A over the mass times u minus v squared. So that gives us our acceleration term as a function of the fluid density, the area of flow, the mass of the trolley, and the two relative velocities. And like I said, this is why momentum can be tricky, because it gets hard to really grasp the reference frames in defining some of these balances. And so are there any questions? I strongly recommend you kind of look over this example until you can kind of understand how each of the terms were derived. And if you're still a little confused, I completely understand. I'd be more than happy to find another way to explain some of these things. But like I said, I really want to stress that this is probably one of the trickiest concepts that we discuss in this fluid mechanics section of the course. All right. So let's look at another example, because I think the best way to look at momentum balances is just working through examples, trying to define the systems, figure out what's the key flow terms, the key forces that we also have to consider. So for this one, we just have a water jet striking normal to a fixed vertical plate. The diameter of the jet is 10 centimeters. The velocity it strikes the plate is 15 meters per second. So what is the force of the jet acting on the plate? So for this one, I'll go ahead and put you guys in some breakouts. And you can spend a little time talking and see if you can come up with the force in newtons of the jet striking the plate. How's it going, Elahi?
It's good, thank you.
Doing your walk around to the lab?
No, I'm actually walking to school right now. Still haven't gone to campus yet. Can I ask you a question as like professor?
You can.
Okay, so what time do you prefer to get an email from a prospective student? Is there like a
That's a hard
preference
question.
among? So like, I don't know, do you like to get emails on Friday, or do you prefer that person to send you that email on Monday instead of Friday?
Probably Monday instead of Friday, but to be honest, most faculty don't really like getting unsolicited emails from students. The best way to do those kinds of things is if somebody else kind of acts as an intermediary and introduces the student and say, hey, I know so-and-so, he's interested in joining the lab. Do you think it would be a good
Yeah.
idea to talk to, for him to be able to reach out and talk with you? Just because we always get
Yeah,
so many, a lot of us just kind of ignore them.
Yeah, it's just like I'm mainly looking at Canada, and Canada's like part of the application process is to have a supervisor. So like schools say that don't even apply if you don't have a supervisor already.
Yeah.
When you look at their websites, they're like, just email us, but like I haven't gotten any like responses yet. So it's just kind of like what to do. I don't know, but I just don't know anyone to like tell them, can you please talk to that person for me?
Yeah. But yeah, probably in the beginning of the week more so than the end.
Okay. Thank you.
Of course. Hello, hello. All right, we got everybody back. So how did it go? What did you guys get for a force?
I got 17,067 newtons. I mean, 1,767 newtons.
That is correct. So in this case, this one's pretty good. These are the types of problems students like to see on quizzes and exams, right? Where we just have a simple mass flow rate and the force. If we're looking at just a simple mass balance in the x direction, if the plate's not moving, then the mass flow rate times the velocity it's striking the plate at plus some unknown force has to equal 0. So essentially what you're looking for is that resistive force, which in this case is going to be rho u squared a, which for this system we had water. Velocity was 15 meters per second. And the area was, what was it, 10 centimeters, 0.1 meters. So that force is simply 1767 newtons. That's not so bad. I'm glad you guys did well. Let's look at a little bit more complicated one, which will help you on homework. So this figure shows a 0.7 pound mass reducing elbow through which water is flowing in at 6 feet per second with a pressure of 3 bar, assuming the 3 bars happening on both the inlet and outlet. Determine the retaining forces Fx and Fy needed to hold the elbow in place.
Why is it called reducing?
Why is it called a reducing elbow? Because the diameter in the inlet, or A, is 2 inches, and the diameter at the outlet of B is 1 1/4 inches. So it's reducing the flow area. If that was a terrible drawing. All right, so this diameter is 2 inches. This one is 1 1/4. The system is going to be the elbow. And we have a pressure here of 3 bar. I could write today, pressure here, 3 bar. And the weight was what, 0.7, or mass was 0.7 pound mass. And it's flowing in at 6 feet per second. So we need to identify the forces in both the X and Y direction. To hold this elbow in place, which means we need to do 2 balances, one in the X direction and one in the Y direction. So let's start with the force for the balance in the X direction. So what types of forces do I have involved in the X direction?
We have the 3 bars that are coming in, and so we just have to multiply that by the area to get the force.
So I have the pressure in times the area. What else do I have in this system? Here, I'll try to clean this up. This does look disgusting. Is there any other forces or momentum carriers involved? We also have the mass flow rate of the fluid coming in at its velocity. And so if this elbow isn't going to move, we have to have some sort of restoring force to keep these from moving. Now the pressure is going to be exerted in the positive direction. The momentum is going to be exerted in the positive X direction. So this resulting force is most likely going to be in the negative X direction. Something to keep in mind. So the pressure is 3 bar. Which I wanted to convert that to PSI, is about 14.5 PSI. So I would say 1 bar is 14.5 pound force per square inch. I would also like to convert that square inch into feet squared and say that there's 144 square inches in a square foot. And then I can multiply that times my area that it's being exerted, which is the diameter of the pipe, that cross-sectional area. So I would have pi times 2 over 12 feet squared over 4. And that would be my pressure times my area force. And that final unit, doing a quick unit check, the bar goes away, the inches squared is canceled here, feet squared is canceled here, and I'm just left with pound force. Now I have my fluid flow, which, assuming this is water, my mass flow would be rho times U times A, which would be the density of water, 62.4 pound mass per cubic foot, times my velocity, 6 feet per second, times the area, which is pi times 2 over 12 feet squared over 4, times the velocity again, or I can just square it here. But I have pound mass and I need pound force. So I divide by 32.2, pound mass foot per pound force second squared. And that leaves my answer in pound force. So all of this will equal my Fx, which would be negative on that side of the equation. So if I do all of this calculations, I should have Fx is equal to negative 138 pound force. Now I can look at the y direction. So what forces are involved in the y direction?
You have the pressure times area again.
The pressure in the area again. Is it going to be positive or negative?
Negative.
It will be negative. What other forces do we have?
Gravity.
We have the force due to gravity, which is it going to be positive or negative?
Should also be negative.
Negative. All right. So then we have the mass of the elbow times gravity. Any other forces?
Would we be left with the restoring force?
We do have the restoring force, which I'm going to make positive for now. And we also have the flow rate moving out, which in this system would be negative. And so that tells me Fy is equal to the pressure, gravity, and the momentum transfer due to convective flow. And so plugging these values in, I have my 3 bar again. Convert it from a bar to PSI. Get rid of the inches squared. Bring my area back in. My mass times gravity, it was 0.7 pound mass. And in order to convert that to mass pound force, I multiply times G over G sub C, which is going to be unity. So that 0.7 pound mass is also a 0.7 pound force. And then I add my flow rate, which I do not have the velocity of the fluid leaving the system. I know it's 6 feet per second coming in, but it's not 6 feet per second leaving because the diameter is smaller. And so that U out is essentially equal to 6 feet per second times essentially 2 inches squared over 1 1/4 inches squared, which is just I got 15.36 feet per second. So I'm going to have 62.4 pound mass per cubic foot times the velocity, or the velocity squared to make things easier, times the area, which is pi, times 1 1/4 divided by 12 to get it in feet. And here, I'll just do 1.25 because it's a lot neater, over 4. And so I know I keep having to zoom out, which if you've noticed, that's just kind of my trend when I do notes is I end up zooming out more and more. So I have my pressure term, my gravity term, and my convective flow term. If you do those calculations, Fy should be equal to 53.6 pound force, and it's positive. So that tells you that the X direction restoring force is to the left, and the Y direction restoring force is up. And so if you wanted to get the total force, you just have to do, good old Pythagorean theorem, the square root of x squared, fx squared plus fy squared, which in this case would be the square root of 138 plus the square of 53.6 pound force. Which should be, let's see, about 148 pound force. Any questions on that example? So when you're looking at these balances, you can break them up in the X and the Y direction. It makes it a lot easier. And you have to ask yourself.
Question.
Yes, go ahead.
When you're accounting for the pressure in the Y direction, why did you use the area of 2 inches?
Oh, it shouldn't be. It should be 1 1/4.
Okay.
Thank you. That's a quick fix. Thank you for pointing that out. So you just need to break it out into the X and Y direction, identify the key terms, plug in and solve. All right, so Mitch, I see you asked, why are we adding in a placeholder? Well, I'm adding in a placeholder because I'm assuming that in this essentially momentum balance, the momentum has to be conserved because I don't want my reducing elbow to move in my system. And so if it's being held in place, the change in momentum of my system is 0, which means there has to essentially all the momentum transfers and forces involved have to be balanced. And so what I'm saying is, if that's the case, there has to be some sort of restoring force. And if so, by putting in this placeholder fx and fy, I can identify, one, is there a restoring force necessary? Because if I do all these calculations and fx is 0, that means the system's balanced without having a resisting force necessary. And if it's not 0, that tells you the magnitude and direction necessary to keep that elbow in place. All right, I think we have time for one more example. So in this system, we have a figure and it's showing a rocket whose mass, which is m, and whose velocity is in v per second. And this rocket is essentially being ejected through combustion and extraction downwards of a certain sort of fuel with a mass flow rate of pound mass per second and a velocity u relative to the rocket. And so we're saying if the gravitational force is of g and a drag force, which is kv squared, how can we perform a momentum balance on this rocket to obtain the expression for the rocket's acceleration? So this is a little similar to that trolley, just a tad different. And so what we're looking for is to identify in this system, what is the momentum balance going to look like, and how can we derive this balance to get an idea of the acceleration of the rocket. So I think for this one, I'm going to go ahead and give you guys a few minutes to kind of think about it and talk about it in some breakout groups. And then we'll talk about it as a class. And see if we can work on it with the rest of today's class time. All right. Bring everybody back. All right. How'd it go? So were you guys able to develop a momentum balance? Well, hopefully you guys identified that the momentum isn't conserved because we're looking for an acceleration. So we can once again consider looking at change in mass with respect to time, times mass times the change of velocity, which is the acceleration we'd be looking for. So what forces are involved in this system? We have gravity, which is the mass of the rocket, times gravity. We have a drag force, which is resisting it. And we have the force as a function of the propellant ejection, which is u minus v, if it's leaving at a velocity u with respect to the rocket, which is at velocity v. And this equals our change in momentum terms. Here, I'll just write A, it's a lot easier. So the other question then I would say is do we have any mass leaving the system of the rocket?
The propellant.
So we're losing propellant. So this would be some negative m that we have in our system. So expanding this out, I have the mass of the rocket times gravity minus kv squared plus mass times u minus mass times v equals negative mass times v plus ma. So since mv shows up twice on both sides of the expression, the good news is it cancels. So what I'm left with is mass times A is equal to negative mass times gravity minus kv squared plus mass flow rate times u. And this is a different mass. I'll make it capital because that's mass of the rocket in terms of as compared to the mass flow rate. So that means our acceleration is simply gravity plus the mass flow rate minus the resistive force over the mass of the rocket. And that's what we have for our acceleration term. Or the only real positive value is that mass flow rate times the velocity of the propellant, which is resisting both gravity and our drag force. Any groups get something close to this? Maybe, maybe not. Like I said, this concept's a little tricky and it can be a little uncomfortable just to kind of get your mind around it. Well, that's all I have for today. Any last minute questions that I would be more than happy to answer? If not, then I hope you guys have a wonderful day. If you need anything, feel free to reach out to me. I'll be available a little bit this morning, probably not this afternoon. I have some things I need to take care of. But as always, feel free to reach out via email and I'd be more than happy to help. Don't forget, I did push back the homework since we didn't really get to talking about momentum until today. So the assignments and the quiz will be due on Sunday. All right. Take care, guys. Have a great day. Thank you all for listening and for attending.
Bye, Dr. Lopez.
Bye.
Thank
Take care.
you.
You're welcome. Take care.